Alright, so let's get started, okay? So we started looking at online learning last time, but I'm going to just step back a little bit. So what we are going to do this week is, or the 2 days of this week, is analyze machine learning problems, okay? So that's a very important area within machine learning. This is not analysis of the algorithms themselves, but more about the problems, okay? So when I say problem, it essentially means the type of concept, okay? So we've been talking about this concept space, this entire concept space, which can be really big. And then we also talked about inductive bias, in which we limit our concept space, saying, okay, let's only look at conjunctive concepts. There could be other types of concept classes as well, right? So what we are going to do now is trying to analyze these classes. So we are trying to understand what problems are more difficult than others. Though the way it will help you, help anybody, is that helps you sort of set expectations about, okay, how well would my machine learning algorithm do for this type of problem, okay? So it's not like a machine, there is a magical machine learning algorithm, right? So the same algorithm might do very well on one type of data set or one type of problem and not do very well in another scenario, right? And the reason being that the inherent problem that it is trying to solve might be more difficult in one setting or another, right? So we are going to characterize these concept classes or the problems in terms of how tough they are, how difficult they are, and then that helps us understand, okay, how well would we expect any machine learning algorithm to do on that problem space, all right? So as I said, the reason we are doing this is to understand the complexity. We are trying to say, okay, this is a harder problem, this is a simpler problem, and so on. We have already done something like that earlier when we said that, you know, learning from a concept class which contains everything is more difficult than learning from a conjunctive class, because a conjunctive class is smaller than this big class, right? So conjunctive space was 3 power d plus 1. That was the number of concepts you can have in that, and the total class was 2 power d, right? So that's one very simple analysis that we have already done, but now we are going to do it a little more mathematically, okay? So the idea is we want to get some bounds on what would be the worst case or best case performance on that problem. Now the first question comes is, how do you measure the complexity, right? What does it mean, complexity of a class? And it turns out that there are many ways to do that. So one way is maybe, okay, how much training data do you need to learn a concept of this class? That could be one measure. Another measure could be, how much resource do you need? Is it how many CPU cycles, how much memory does it need? Because you don't want if a class needs a lot of CPU cycles, then you know that it's a more challenging class than something else, right? That could be another metric. The last one is number of mistakes you make. Now this is mainly for online learning, and we looked at it. I'll tell that again, but this is more about how many mistakes would you make before you have learned you have learned that class, right? It's like that song, how many roads must a man walk down before you call him a man, right? The same thing here. How many mistakes would you expect an algorithm to make before it's really learning, before you call it a true learner in that setting, right? So we are going to use that metric today for online learning, and then I think 1 week or after 2 weeks we are going to come back and look at a slightly different metric as well. Any questions so far? I'm sorry, could you be louder? I have to first locate who's why is important? I see. So your question is, why are the number of mistakes important? Right. So because for online learning, right? So that's a very good question. So the question is, why do we care about the number of mistakes you make? The reason is because we are looking at online learning algorithms. So they work like this. So the online learning algorithm is slightly different from what we have seen so far. The idea is that an algorithm keeps on getting data and refining itself, but while it is learning, it is also being used for predictions, right? So for example, let's go back to our example of benign and malignant tumors. So let's say you're training a robot to differentiate between benign and malignant tumors from MRI scans, right? Now, day one, when you start, that robot knows nothing, right? Of course, it will make a lot of mistakes, but as you give it more and more data, right, you want it to learn, but at the same time, you are also going to use its predictions for whatever medical purpose, okay? So that means that you do not want it to make too many mistakes, because every time it makes a mistake, there are some consequences in the whatever domain you're using it, right? So that's the reason it is important is because of the way you are using that system. You are using it in an online setting, which means that while you are learning it, you are also using its predictions to do your stuff. You see what I mean? So that's why we want to minimize the number of mistakes. We want to minimize the number of mistakes before it reaches a point at which it won't make any more mistakes. All right? So that is the reason. So let's look back at our online learning setting again. This is, I went through this, right? So this is about online learning, but let me now go back to I don't know, the slides are out of order, but anyway, this is what I wanted to talk about. So how do we put a mistake bound for a class of problem, for a conjunct or for a concept class, okay? So we are going to first start with how do we put a mistake bound on an algorithm. So let's say this fancy L denotes a learning algorithm, for example, candidate elimination. Of course, right now I'm not talking about online learning. This could be any learning setting. So any learning algorithm, a neural network, logistic regression, and you're trying to learn a concept small of C which belongs to a concept class fancy C, okay? And let's say in one setting you get one sequence of training examples that is denoted by D, okay? So you can measure the number of mistakes that you make to learn C with D example. So if I go back to the online learning setting, see, if you remember, what we do here is that we have a training data that is coming one by one, right? And for every time you get a training example, x of I, x superscript I, you first predict, okay? You first predict using whatever you have learned so far. That is your C star x of I, which means this is your prediction right now, right? And then after that, then you are told what really C of x of I is. And then you adjust your algorithm and you go back. So if you make a mistake here, right, if this is not equal to this, then that's called a mistake. Now that is where there could be some cost, right? So going back to your question, this is where I could say, hey, you know, you're making a prediction and then you're giving this report to the doctor saying, hey, this is malignant or benign. So if you're making a mistake, there will be some consequences there. So you want to minimize that such that at the end of it, after you have exhausted your training data, you say, now I'm perfect. Now I'm not going to make any mistakes. So we want to discover that C with minimum number of prediction mistakes, right? So going back here, so you can, for a given data set, you can measure how many mistakes you make. That is denoted by M of L C comma D. Okay, let's just call it a function. That's a number of mistakes made by this learning algorithm to learn C with D examples. All right. So we assume that yes, eventually it will learn that C, but how many mistakes it makes is quantified by this number. But that is not a good measure for that algorithm, because what we have seen in the past too is that it totally depends on the training examples. You might get a really bad training data set in which you would make a lot of mistakes. You might get a very nice data set in which you might make 0 mistakes and learn the concept, right? So what we do is we take a max of this. We say for all possible training data sets that you can get, right? What is the worst case scenario? What is the worst mistake? Go ahead. Question? Right. Yeah. So the question is, what do we mean by all D? So D includes all ordering as well. So you're right. It also matters what the sequences, as I said, right? So D is one possible sequence. Another D could be the same examples but in a different order. So we have to consider all possible permutations and combinations of elements that are in X, right? So this quantity quantifies what is the worst case performance of this algorithm to learn C. Okay, so now we have taken D out of the picture, right? So it doesn't depend on D anymore. That's the worst case scenario. And the next thing we want to do is we want to look at the performance of this algorithm on any C that belongs to that concept class. Okay, so that is this number. This is the worst performance over all C that belong to this concept class. So remember, a concept class contains many concepts, right? Now C could be any one of them. Some of the so for example, in the case of conjunctive concepts, right? Let's go back here. So if just a side note, in the videos you would see that whenever I switch to this, it sort of goes a little out of focus, but I've set this to autofocus, so that should help. Okay, so let's say this is your C, which is all conjunctive concepts. Okay, and let's just take an example of our tumor example, right? So one of the concepts here could be small question mark dark question mark, right? That could be one conjunctive concept. Another concept could be small, large, small, thick, irregular, dark, question mark, something, right? So these both are conjunctive. They both belong to the same concept class, right? But for one of them, the algorithm might take fewer mistakes. For another one, it might make more mistakes, right? For example, if your concept was something which had everything, the most specific concept, large and something, I'll just write, well, let's say these are all our smooth. So this is another concept. This is an easier concept, right? Because here it's so specific that as soon as you maybe you might not make too many mistakes to learn this one. This might be a little harder. The most general might be even harder, right? So it depends, right? So what this number does, let me switch back. The last entry is it tries to characterize this algorithm over all possible concepts, over all possible data sets. So that's the worst case that this algorithm would do in any setting within that concept class. Okay, any questions so far? All right. Now one thing you can already note is that it's very hard to compute this, right? Because if you try to do it in a naive, exhaustive manner, you would have to consider all possible concepts, and then you would have to consider all possible permutations of the training data set and then compute the worst case, right? So it's not a very trivial task to do. What we will see today is that for some algorithms, you can actually compute this just because the algorithms work. For some algorithms and for some types of concepts, so not for everything, for some types of concept classes, okay? All right. Now remember, in the beginning I said that we are not going to characterize algorithms. What we want to characterize are the concept classes, right? So now comes this notion of an optimal mistake bound, which goes over all possible algorithms and tries to find the best algorithm, the algorithm whose worst case bound is the least, right? So that tells you the complexity of the concept class, okay? Because if you have a concept class and you let's say you have figured out that this algorithm gives you the best or the lowest worst case complexity, then you can say, okay, nobody else can do better than this on this concept class, right? Which means that you have now put a lower bound and say, okay, you cannot do worse than this, or you cannot do better than this, because that's the, out of all the possible algorithms, this is what it does, right? Now you can see another point here is that this is sort of a very theoretical construct, but you cannot really compute this exactly, right? Because you have to go across all possible algorithms that there are, right? Which cannot be done, because there could be just so many algorithms, right? So you cannot exhaust or enumerate all algorithms, which means that you cannot exactly compute this, right? But what we can do is that we can set bounds on this, so a bound on this bound, right? So here is this figure, my favorite figure, is that let's say this y-axis is counting the number of mistakes, right? Now for a concept class, this is what you want, that opt of C is what that opt of C, right? As I said, because you cannot enumerate all possible algorithms, you can never compute this, right? But what we can do is that we can come up with bounds on this. We can say, okay, the opt of C will be smaller than this and smaller than this and smaller than this. So that way you can characterize them. So I'll show you how to do that. Any questions so far? All right. So of course, one simple bound that you can set is 2 power d if you have binary attributes. The reason being that that's the total number of objects that you can have, right? So that's the total number, that's the maximum number of mistakes that you can make. So any algorithm cannot make more than that mistake, right? That means even the best algorithm would not make more than that. That means that 2 power d will always be greater than opt of C. So that's one bound that you have put, right? That's a very trivial bound that we have put. Another bound that we got to put is, so of course that's too loose, right? You want it to be tighter, because this would be true for any concept class. So if you want to compare two concept classes, right, you ideally want opt of C1 and opt of C2 to know which one is harder, which one is easier. But both of them are bounded by 2 power d, but that doesn't help you, because then both of them are equal, right? So you want tighter bounds. So the way to do it is we try to find one algorithm, some L, and compute ML of C. Remember, ML of C is the worst case scenario for L in learning any concept in C, right? So if you can compute that, then you know that if there is a better algorithm, it would be lower than that, right? So now you're setting bounds on it, right? So that is the trick to set these bounds. Any questions so far? So that's a very important concept, especially if you are sort of going to work in a little bit of theoretical machine learning or analysis of such algorithms. This is a very key step there, right? So you're trying to find out algorithms. So this is what we will do today, is we will come up with algorithms, or we will see some algorithms, and we will come up with their ML of C, and then that will help us put bounds on this this thing, all right? All right, so one possibility is, actually we have already seen a flavor of that. So remember that list then eliminate algorithm. If you run it in an online setting, and I'll tell you how it runs, then you can say that the number of mistakes it will make on any data set, on any concept in that class, will be the size of the concept class minus 1. Why? So remember, what is list then eliminate? What it does is that every time you see a let's see, so I'm going to call it online list then eliminate. So it starts with the entire concept class as your version space, right? It says, okay, everything could be, I mean, my true concept can be anywhere here. Then it gets a data point. Step number 1, it gets some x and c of x, right? And then what it does is it tosses out all the concepts from here that make a mistake on this example, right? So it goes through each concept here, each hypothesis that's inside, and then it computes the h of x. So it takes for all h belonging to this C, if h of x, now h of x essentially is the prediction that you get using that concept, is not equal to C of x, then remove h from C, right? And then you keep. So what happens is that you might make some mistakes before that, right? So first what you do is you say h of x is your C of star of x. and now you want to count how many mistakes can you make, right? Now what you can easily see is that because you start with C, capital C, size of C concepts in this class, right? So the number of mistakes that you will make will be cannot be more than C minus 1. The reason being that if you make more than this mistakes, that means that this set becomes empty. But since you know that your target C belongs to here, that means that at some point you would only have that left, right? So you cannot make more than these many mistakes. All right? When you do your gradients quiz, one of the problems is actually this algorithm. So this will make you, that will help you understand this little more. But that's actually again a very trivial bound. This is still too loose. All right? So I'm going to go back. Any questions? All right. Oh yes. Yes, you're right. Yeah, I'm a little messy with the notation, but yeah, you can. This is not. Yeah, you're right. Yeah, so this is whatever concept after making your inductive bias, whatever you start with that. But yeah, exactly. You're right. Yes. Right. Yeah. So this is sort of. I always hope people will understand if I wave my hand too vigorously. But the idea here is that, see, I mean, it's actually a very trivial kind of concept. So the idea is that here, right, how many concepts do you have in the beginning? You have C concepts, right? If I call it C, one of them is your small c, right? Now, when you get a training example, the way this works is when you get your training example X, you take some concept from this, one concept from this, and then you make the prediction based on that, right? When you make a prediction based on that, you can either make a mistake or not make a mistake. So if you make a mistake, you will toss that concept out of the set, right? So every time you make a mistake, you will toss one concept out, right? And there are only these many concepts. So the number of mistakes that you can make before it becomes empty is C, size of C. But of course, one of them is small c. And on small c, you will never make a mistake, because that's the concept that generated that training data set, right? So which means that the number of mistakes you will make before you are only left with small c cannot be more than C minus 1, right? Okay. So that is another bound that we have set. What that means is that we know there is an algorithm called online list and eliminate, which makes these many mistakes on any concept in this class, right? So that's another bound that we have set. So now let's say, can we go even tighter than that, right? So what I will show today are actually one of these algorithms, but there are two algorithms. One is called halving algorithm and one is called randomized halving algorithm, through which you can get even tighter bounds, okay? But these are only true for conjunctive concepts, of course, but for conjunctive concept classes, you can get even tighter bounds. Well, actually, these are not for conjunctive, these are for anything. So halving algorithm is one algorithm that lets you get another bound. So let's look at that algorithm and then we'll analyze it. Okay. So this is the halving algorithm. What it does is it tries to, at any point of time, when it sees a new training data, right? Again, apologize for the notation here. So what it does is that at any point of time, when it gets a training data point X, it splits its version space into two parts. One are those hypotheses which agree with X, and one that do not. So sorry, one that call X positive and one that call X negative. So there will be two at any given point, right? And then what it does is it sees which one is bigger, and it uses that as the prediction. okay, and then when it uses that as a prediction, then it gets the true label, right? So let's go through this here. So this loop is basically, it's going through the training data one by one. So at any point, this v subscript I minus 1 is the version space having seen I minus 1 data points, right? So this is the size of that part of your version space which calls x positive, okay, or malignant, and this is the part that calls x benign, okay. So here it checks which one is bigger, which means which right now my version space is giving a majority decision of one type, right, and it uses that information to make the prediction. So if this one is bigger, it calls c of x of I as 1. It says, okay, the prediction is that it is malignant or 1, otherwise it's 0, right. Now it gets the true label. Now it checks. Now this is where it checks if it has made a mistake or not. So if it does not make a mistake, it does not do anything, right, it just keeps going. But if it has made a mistake, then it removes the set that led the mistake, right. So for example, let's say it has made a mistake. It means that the majority set was wrong. So it tosses all the hypotheses that are in that majority set from your V. So now your V becomes smaller, right, and it keeps going. So I could give you a proper proof for this, but that's sort of, we don't want to do that in that detail. But you can think about it. You're all you have all done algorithms courses, right? So what you see here is that every time at least half of the items are being tossed away. That means that in log of, right, the log comes there of the size of C, because that's what you start with. In those many steps, you would be left with one concept, your target concept. Okay, that's sort of a very very vague proof, but you can go through the steps. I think in the notes I have step by step, or I can give it to you if you want, right? But the idea is very simple. So let me show it to you in a written matter. So here is what is it, halving algorithm. So what halving algorithm does is that it starts with, so your V naught is actually the concept space that you are starting with, your inductive, after your inductive bias, right? Then you get an X, your training example, and what you do is, looking at this X, you split your version space into two parts. These will be all the hypotheses which call h of x equal to 1, and these are all the hypotheses that call x as 0, right? I mean, and it need not be half. It could, I mean, exact half, right? It could be maybe all of them are calling it as 1. That I cannot guarantee that, right? So they could be of any size, but it would split it into two parts, right? Then what you do is, then you say that my prediction, the prediction will be governed by which side is bigger. So let's call this and this. If this is greater than this, then this will be 1, because this side is bigger, right, and so on, right? What you and then you look at C of x. This is the actual label. Now what happens if you make a mistake, right? If you have made a mistake, it means that the bigger class is wrong, right? So you're going to toss the bigger class out, right? So at every mistake, what you're doing is you are tossing out at least half and more, because of this decision, out, which means that after log of, and actually it could be less than that, but after log of C mistakes, you would reach your target concept, right? So that's the basic proof, but you can mathematically also prove that. Any questions so far? All right. So what this lets us do is, it lets us put even stricter bound on our worst case complexity here, log of 2c, right? Then there is another flavor of halving algorithm which does some randomization, which actually gets you even tighter bound, log of base base of e instead of base of 2, right? We won't look at that here, but the idea is that this is how you characterize the worst case performances. All right. All right. So let's go here. All right. So this is a good algorithm, halving algorithm. It gives you a pretty tight bound, but the problem with this algorithm is that it's pretty computationally expensive, because at any given time you need to start with your entire version space, right? Your entire version space. Oh, sorry. Go ahead. Right. So. Right. Yeah. Yes. So the question is, does the halving algorithm guarantee that you will reach the target concept, right? The answer is yes. If the target concept is in that space, if your inductive bias holds, right? If your C is in that big thing, then you will reach it. The reason being that, and that's actually this another, what is the same one? One problem in gradients actually sort of will help you understand that more. But if you look at it, right? If you look at your halving algorithm, so we start with this, whatever your inductive concept space, I mean your concept space is, C. Now if your C, the correct C is present inside the C, that assumption has to hold, of course, right? Now what will happen is that you can be guaranteed that every time when you make that split, so whenever it's a mistake, this will not be in the majority class, which means that this will never be tossed out. The correct concept will never be tossed out. That's, I mean, you can think about it a little more, but see, if, let's say you get some x, right? And later you'll also get its true class. Now if this x was generated by this concept, right, it means that this would not be in the majority class when you're making a mistake. That's sort of the something that maybe you can work it out a little bit. If you sit down and think about it, you will know that it will never happen, or if you do the gradients quiz as well, it will never happen that C, the true concept, is in the majority class when you make a mistake, which means that it will never get tossed out. If it never gets tossed out, then at some point it will happen that you would have converged to that. You see what I mean? So this is guaranteed to give you the right answer, but you don't know how many steps it will do it, but it will at least do it in not more than log C mistakes. So those are the proofs, those are the numbers that it can guarantee. But that's a good question. So I will ask you to work through that gradients problem. It will help you understand this whole thing a little more. All right. So this is a good algorithm, but it's not very computationally feasible, because at any time you have to maintain that version space, and whenever you have to maintain a version space, it becomes horrible, because version space, even for a restrictive concept class like a conjunctive concept, is 3 power d plus 1. So if your d is in a realistic setting, if your number of attributes are 50, 60, then it's very hard to store it, right? Which means that it's not a very good algorithm in a practical setting. So now, so next question becomes, are there any efficient implementable learning algorithms which you can implement efficiently but also get similar mistake bounds? Okay, so we're going to look at one of them, and this probably is the first algorithm that we are going to look in this course, which is practical. All right, but to do that we have to first make some assumptions. We cannot do it for any concept class. Okay, halving algorithm doesn't make any restrictions on the concept class. It can be for anything, but we are going to look at one algorithm which lets you make guarantees. It is implementable and everything, but it is not it's not for any concept class. So this one is for a specific concept class called monotone disjunctions. Okay, so like it's sort of we have seen conjunctive concept classes. This is something similar. It's called a monotone disjunctions of at most k variables. So that is our restriction. Okay, so what is a monotone disjunction of at most k variables? It is basically the concept would have this form. It will be an OR. Disjunction is an OR of k or fewer attributes. So let's say you have d attributes. A monotone disjunction would have a few of those, or k of those, or lesser. It's k or at most k. And it's a monotone disjunction. It means that it's an OR, and monotone means it only takes the positive values. So for any attribute, defining this is a fantastic pen. All right. So what is a monotone, k monotone disjunction? It means that the concept would have a special form. It could be something like small. Let's say you have d attributes, right? So you can take k of those and only use the positive value. So remember that when we have binary attributes, right? So it could be small or large, dark or light. But earlier I said that you can also treat them as 1 or 0. One of them is positive, another one is not that, right? So if you treat them as that, then you can treat this. So let's say you have d attributes x1, x2, x3, xd, and we are going to say that each one of them can take a value x1 or x1 bar, right? So this could be like dark or not dark, things like that. It's just for analysis. So in real setting, you can you can use one of the values as positive, it doesn't matter, but you have to be consistent with that. Okay, x2 or x2 bar, so on, xd and xd bar. All right. So a k monotone disjunction would be one which takes k of these or fewer. So it could be x1 or x3 or x4. That's it, right? It could be x1. It could be nothing at all. It could be k of these, of course, but these are all allowed, but this one is not allowed. x1 or x2 bar, not allowed. It's just the restriction that we are putting on this class. What else is not allowed? x1 bar is not allowed. x1 or x2 and x3 not allowed. So it has to be disjunctions, it has to be monotone, and it can only be k of these. It cannot be x1 or x2 all the way to xd, where k is less than d. This is also not allowed. Okay. But any smaller thing is allowed. Okay. So what we will see today is that in that setting we can actually come up with estimates on the mistake bound to the same thing as halving algorithm. So it's going to be log of the size of C. But first let us look at what is size of C, right? So remember that this is sort of we have done size of C for conjunctive concepts, right? We said that for conjunctive concepts the size of C is 3 power d plus 1. Now for k monotone disjunctions, what is size of C, right? That's the question, right? So if you think about it, right, what this the way you construct these concepts would be, you take k or fewer items from a basket of d items, right, and then you put together. So first thing you can do is you can take 0 items. So how many ways can you take 0 items from d attributes is d choose 0. You can take 1 item, you can take 2 items, and you can take k items, right? So this is the size of your concept class. Okay. and you can work it out. This works out to somewhere I had that number. It's k log 2 of d. Oh, sorry, exponents of this. So this works out to this. You can do the addition, or at least an approximation. Yeah, it's an approximation. So it's basically so it's nearly equal to this, right? So this is your size of concept class, and what we will what we can prove. Yes, go ahead. Right. Right. Yeah. Sorry. Yeah, that's true. The question is that sometimes I use 0 and 1 for denoting attribute values. So, well, so we can say that 1 means positive and 0 means negative. Basically, it's just a way to differentiate between two values, and we just take one of the values. So let's assume from now on that when you have binary attributes, they either take positive value or negative, true or false, presence or absence, something like that. Yeah, I apologize for that. There'll be a time when I'll be more consistent. All right, so here we are. So this is the size of my concept class, and now what we are going to do is put a mistake bound on this. We are going to prove that you can do this. The opt of C is less than equal to this, which is the same as halving, right? Which means that there is some algorithm whose mistake bound is this much. That means that the optimal algorithm would have less than that, right? For any C in this is fancy C. Now this C, of course, is k log 2d exp, which means that we can show, this is from here, right? Which means we can show that opt of C is less than equal to k log 2d. There is an algorithm for which this is the mistake bound. Okay, that's what so that algorithm is what we call Winnow algorithm, right? So we're going to look at Winnow algorithm, but we will not do the analysis, rigorous analysis in class. In previous courses, I used to give that as an homework, but this time we do not have that homework. So I will put that as simple questions in gradients for next week. So that will help you understand it. But let us look at Winnow algorithm, because it's a sort of a first algorithm that we are looking that we can actually encode, right? 4 more minutes. So I'll just get started, but then we'll look at it more later, right? So one thing we can see is, so now here we are going to look at something called linear separation, all right? A linear separation. So now we are going to geometry, all right? So if we think of these these points, these data points, like these tumor examples, as points that we can place in a coordinate space, right? Then a concept can be thought of as a line that you draw in that, such that everything that is on one side belongs to the concept and everything that's on the other side does not belong to the concept. Okay, so this is an important sort of first step, because from in the many of the algorithms that we will learn later on have the same form, right? So I'm going to briefly introduce this notion of linear separation. Okay, so let's say your data is, you can map the data into this two-dimensional space. Let's say your data only has 2 attributes. Okay, of course, if it has D, then you're looking at a D-dimensional space, but the best we can do on paper is 2-dimensional. So now, since these are all binary data points, right? So if it's a 2-dimensional space, you can have 4 data points. One which is like this. Both of them are not 1. one of them is 1, one of them, the other one is 1, right? So you can have 2 power d equal to 4 data points, right? You can put them in this space, right? So for example, let's say whenever it is a naught, let's call it 0, right? That means that this point will be this one. This point will be I could have also called them -1, 1. It would have just shifted it here. But the idea is that you can map these binary points into this space. Now what we are going to say is that if there is any concept, so what does a concept do? A concept essentially labels these, right? So a concept could call all of them as positive, all of them as negative, all of them, 2 of them positive, 2 of them negative, right? So a concept which calls these 2 positive and these 2 negative, we can draw a line like this which can separate it, right? So which means that this concept is linearly separable, right? Same way, a concept which calls all of them positive, of course then we can draw a line anywhere, and same thing for negative. But if there's a concept which calls let's say these 3 positive and only this one negative, then you can draw a line like this, and that is linearly separable. But not all concepts are linearly separable. So even for this simple case, if a concept labels these 2 as positive and these 2 as negative, then there is no way you can draw a line which can linearly separate them, right? These 2 are negative, these 2 are positive, right? Is that right? Yeah. That's you can never draw a line, which means that this concept is not linearly separable. What we will see in next class is that a k monotone disjunction will always be linearly separable. You can always draw a line, which means that this weird concept can never be expressed as a k monotone disjunction. Okay, any k monotone disjunction can always be separated by a linear line. Okay, and that will help us come up with our Winnow algorithm. Any questions so far? Yes, go ahead. Right. So the point is that any concept will have the effect that a concept has is that it labels them, right, in some way. So we are basically going through all possible concepts, and each one is giving you some labeling. Some of them will be linearly separable, some of them will not be. The point is, and we will see it next time, is that if it is a monotone disjunction, if the concept belongs to that smaller class of monotone disjunctions, then you can always draw a line. All right? Any other questions? Go ahead.
How do you know where to draw the one point? Could it be like an x equal to something at some value or something?
Yeah. In this case, it can be anywhere because these are binary values. So even if it is shifted a little bit, it's fine as long as it gives you a clear distinction. When these values are continuous, then it depends where you draw the line.